Okay, good morning, Year 12 single mathematicians. Just going to continue with mechanics. Last time we did 10.4, so we're on 10.5 connected particles. Going to start off with Newton's third law, which I think I've mentioned at least once before. Every action has an equal but opposite reaction. I'm going to try and just illustrate what I mean by that with these three identical diagrams. So for the first one, just going to consider the forces acting on object B. There you got an object B on top of object A and then a floor underneath. So what forces would act on B? Okay, let's assume that B has a mass, so we would have a weight, and that weight would act directly downwards. Call that W. And object B is in contact with object A, sitting on top of it. And by Newton's third law, every action has an equal but opposite reaction, so there would be a reaction force. Call that RB. And that reaction force is obviously perpendicular to this point of contact. And that's it. There are no other forces acting on object B. Okay, exactly the same diagram. This time we'll label the forces acting on object A. Okay, object A has a mass, so it would have a weight. Call that W. Object A is in contact with the ground, so there'll be a reaction force. Call that RA. But also it's in contact with B, so B will exert a force on it. And that force, by Newton's third law, will be equal to this one. So there'll be a force going down there, which is RB. So there's three forces acting on object A. Its weight, it's in contact with this surface, so a reaction force going that way. As in contact with object B from above, so there's a reaction force going that way, and that reaction force going down balances with that reaction force going up. Now, a third option is forces acting on both. So if you just considered A and B to be one particle, effectively one object, what forces would act on this one object? Well, you'd have the object's weight, which would be these two added together, and then this single object is in contact with the ground, so there'll be a reaction force there. Call that R. So those are the three different options, depending on whether you're thinking about forces acting on B, A, or you treat it as one big object. And we're going to need that in the next couple of lessons. Right, easy number one is lots of writing. We'll try and break it down. So we have two particles A and B of masses 5 kilograms and 3 kilograms respectively are connected by a light inextensible string. A is pulled by a horizontal force of magnitude 40 newtons along a rough horizontal plane. So let's draw a sketch for this. So you've got a rough horizontal plane. Got two particles, A and B. A has mass 5 kilograms, B has mass 3 kilograms, and they're connected by a light inextensible string. A is pulled by a horizontal force of magnitude 40 newtons along a rough horizontal plane. So 40 newtons going in this direction. That's acting on A. Particle A experiences a frictional force of 10 newtons. So friction resists the motion. So there's 10 newtons going in that direction. And B experiences a frictional force of 6 newtons going in that direction. And they've asked us to find the acceleration of this system. So it should be pretty obvious that the acceleration is going to point in that direction. Right, how can you do this? Right, the best way to do it is label all of the forces acting on both objects. So what forces are acting on object A? Well, it has mass, so it'll have a weight, 5g newtons. It's in contact with the surface, so by Newton's third law there will be a reaction force, call that Ra, newtons. And it is attached to this string. Now because A is moving to the left, the tension in the string is going to resist that. It's going to try and pull it back. So tension will be in the string and it will face in that direction. T newtons. And those are the only forces acting on object A. Now if I resolved object A and resolve it horizontally, I can get an equation. Now ask yourself the question, is this object accelerating? Yes, it is. If it is accelerating, out of the three of Newton's laws, which one do you choose? It would be the second one. Newton's second law states F equals ma. F is the resultant force and ma is the mass and acceleration. This is just for object A, by the way. So the mass of object A is 5 kilograms. The acceleration of object A is unknown. There is a second way to work out the resultant force. It's the forces going with the motion, subtract any forces resisting it. So 40 newtons, subtract tension, subtract friction, and then simplify. 30 subtract t is equal to 5a. You got one equation with two unknowns. We do now exactly the same, but this time for object B. Label every force acting on object B. It has a weight, 3 kilograms, so 3 times g newtons. It's in contact with a rough surface, so there's going to be a reaction force. Call that Rb newtons. And again, it's attached to a string. Now think about the string for this one. If I was object B and they started pulling me in this direction, the tension would pull me in this direction too. So tension for B is actually going in that direction. And these two tensions are equal. That's one of the assumptions we make. Okay, so let's resolve for object B. And we're going to do this horizontally. Newton's second law again, F equals ma. Okay, the mass of this object is 3 kilograms. The acceleration of this object is unknown, a. How would you work out the resultant force in this direction? Well, force going with it, the only one going with it is T. Subtract the forces going against it. The only one going against it is the friction, which is 6. And you've got a second equation. Two equations, two unknowns, you can solve them simultaneously. I want to eliminate the t's, and you can do it in one step. You just add the equations. 30 plus -6 is 24. Minus t plus t disappears. 5a plus 3a is 8a. And that gives you acceleration is 3 meters per second squared. And that is actually part A done. Part B, find the tension in the string. Well, pair of simultaneous equations, we work out the second unknown. So if I made t the subject there, t is equal to 3 3's plus 6, which is 15 newtons. And that's the hard bit done. Acceleration and tension, generated two equations, solved them simultaneously. Part C, explain how you've used the model and assumptions light and inextensible. Okay, so inextensible and light is that, I can't remember what chapter it was in the book now, but it was loads of modelling assumptions. Light means the mass is negligible. So in this case, the string's mass is negligible and the tension would therefore be constant. So negligible mass will give us constant tension. And inextensible means it's not going to really stretch. So this is going to give us a constant acceleration for both particles. And that would be part C. Now, I want you guys to practice some of these questions. So if I find out which exercise, it's going to be it's going to be page 171, exercise 10E. And you're going to do question 1. You're going to do question 3. You're going to do question 5. Question 7. And question 8. Now, the only bit of advice I can give you is treat each particle separately. Like I did with easy number 1, you want to resolve for one particle separately, get an equation, resolve the second particle separately, get a second equation, and always solve them simultaneously. And that's pretty much it. If you've got any queries about any of the questions I've just said, so that was 1, 3, 5, 7, and 8, then post a question in the Teams chat and I'll create a video and get back to you.